start recording. So glad to have Raffael Stenzel today talking about higher geometric sheaf theories.
Yeah, hi, thanks for having me. The title leaves a lot of interpretation, I suppose, for the audience. So what I will do is I will proceed in three sections. First, I will recollect a few ordinary notions on coherent categories, and the sheaf theories. Then I will indulge in a little section about motivation, about how that may be insufficient for higher category theory. And then the third section will be about the higher analoga of these things. So let's start with section 1. So ordinary means ordinary categorical. So let's just start immediately with a definition. That is, if we start with the regular cardinal, then one says that a category C is kappa geometric. If first C is regular, so that means it has finite limits, and since it has fullbacks, it has fullback stable image vectorizations first. And furthermore, the subobject cosets or object C and C have kappa small fullback stable unions. So usually there are two edge cases which are considered most often, which is kappa being omega. So in that case, you say that C is coherent, right? So omega geometric categories are coherent categories, and then the other edge case is where we don't prefix any cardinal, and so we say that it's geometric if the subobject cosets have all small fullback stable units. So furthermore, a functor between kappa geometric categories is itself kappa geometric if it preserves all the structure enclosed, so it preserves finite limits, effective epimorphisms, and kappa small unions of subobjects. So a few weeks ago, Christoph gave a talk and gave a great introduction to the category of coherent, or more generally kappa geometric categories and their underlying syntax. So I will reduce this to the fact that every kappa geometric category C exhibits an internal language which is a kappa geometric theory. Which we call TC, such that for all other kappa geometric categories, the initial equivalence between models of this theory in V and kappa geometric functors from C to D. So I will not go into detail what that is because I will basically do no syntax today anyway. This will yield the motivation first and foremost. But remember that a kappa geometric theory is a first-order theory. Again, the operators with an extension quantifier, a conjunction, a disjunction, which allows kappa many inputs, top and a bottom element. And then the theory consists, of axioms, and the axioms are phrased in rules, right? So we might have a formula here, and a formula here, which both are phrased using those operators. And then to set a rule of this form can be also phrased as, in a single formula, which has an for all quantifier in the beginning, and then an implication between those two geometric formulas. Right, so geometric theories of this form. All right, and just to give some context, so examples are manifold. So examples include algebraic theories, such as the theory for monoids, rings, groups, abelian, and the commutative such. Also, furthermore, local rings, torsion-free abelian groups, fields of finite characteristic, and so on. Right? So there are many examples, especially in algebra. And for example, most of those theories are coherent in fact, so they have a finite arity as input for the disjunctions. But if you consider, for example, fields of finite characteristic, you need infinitely many, countably infinite disjunctions to create that. All right, another fact. So if we start with the kappa geometric category, let's see. Then this can be equipped with the canonical coordinate topology, which is generated by the kappa geometric covers. Is this still readable, or am I a bit too sloppy? Okay. So you remember that a kappa geometric cover is a jointly epic family of arrows over a common base, right? So that means that it is a set of arrows indexed by a kappa small set I, such that, what does it mean to be jointly epic? Such that whenever we have a parallel pair of arrows out of C, then they act jointly epic, meaning if, sorry, I didn't give the names. Call them, this is Fi, this is G and H. If for all I these equations hold, then these numbers are the same already, right? So in particular, if C happens to be kappa extensive, or just have kappa small coproducts, then this is the same as that the coproduct of these maps is an effective epimorphism. Which again is the same to say that the union of these subobjects is an isomorphism. Right? So in some sense we impose a colimit condition on subobjects associated to our family. So these kappa geometric covers faithfully generalize the canonical topology on a frame, and hence generalize or categorify topological spaces. Right? So If you remember what a frame is, right, it's the dual notion to a locale. So it's a lattice with small unions and finite meets, which commute. And every frame is a geometric category, and the underlying theories are exactly the propositional theories. So these are the kappa geometric, the geometric theories with only zero error relation symbols. They have no function symbols and no sorts. So we now have a notion of Brownian topologies from these guys. So we have a relation to topos theory, the toposes over those guys. Well, toposes as sheaf theories. And one says that a topos E is coherent if E is the sheaf theory over some coherent category equipped with the canonical coherent coverage. Coherent categories. And so these play an important role both in logic, categorical logic, and algebraic geometry, right? So I think even the term was coined by Deligne in this work on algebraic geometry.
So coherent category is just a kappa geometric category for
kappa equals omega, so finite. So
yeah.
Kappa is always to be thought of as less than kappa.
Mm-hmm.
Right. So if you think of in the definition, I said I want kappa small unions. That means I want unions of cardinality smaller than kappa. Mm-hmm. So in the case of omega, that means finite.
And what do you get if you consider a category which is kappa geometric for all kappa?
That's the definition of geometric.
Uh-huh.
That's what I just said orally and didn't write down.
Right. Okay.
But yeah, that's called a geometric category. Sometimes you impose at least on top that it is well powered. So
okay, I see.
Yeah.
Yeah.
Okay. And then there's the theorem that so there's a special class of toposes which is interesting to us, but there is an exhaustive characterization of all toposes in terms of its framework. Namely, there's the theorem, the classic one, that every Grothendieck topos is equivalent with a category of sheaves for the canonical. Here you have geometric, so this is now geometric for all kappa. Grothendieck, for the topology over itself. Right. So if you start with E, then of course you can embed it into pre-sheaves over it. So these are this is now a locally small but a large category. You can look at you can still look at contravariant functors into sets. And in here, you can look at the subcategory of those pre-sheaves, of those contravariant functors, which satisfy the sheaf condition. Every representable satisfies that, and then one shows that this is the equivalence of categories. Right, so sheaf theories for geometric theories play a central role in topos theory, and especially in the context of the whole setup of classifying toposes, right? Let me maybe, before I move on, add one more lemma in this context. So this was the recollection of the ordinary setup, that you can show that the Cartesian, so this means the left exact functor, between two kappa geometric categories is itself kappa geometric in the definition I gave before, if and only if it preserves the kappa geometric colors. Right? So one way to read that is a functor is logical, so it preserves the logical structure, if and only if it preserves the topological structure. Right? Any questions so far?
So just the ordinary Grothendieck topology on the open sets of a topological space, that's geometric, right?
Yeah.
And that's the usual sheaves are then the geometric sheaves.
So I didn't write down what a sheaf is, I suppose most of you know anyway, but it will be featured later on anyway. Alright, paragraph 2. So there's some motivation to move on from ordinary notions to higher notions in this context. So why do we consider the covers that we do consider here, right? So the covers are jointly epic families, and what is characteristic about that? Well, first of all, we index our diagrams by sets, right? And then having this set index diagram over C, the condition that we impose is a column condition on associated subobjects, right? So in the end, you really only want to manage columns of subobjects. The reason being that the logic interprets relation symbols as subobjects, right? So there is an inherent relationship between the logic that we want to find semantics for and the topology that we perform. Now, monicness, in case that is a word, of relations.
Monicity.
Monicity, is that more of a word? Monicity. Right here. Of relations is an instance of what is syntactically known as proof irrelevance, right? Something that, for instance, type theory is not. So, in particular, as an instance of proof irrelevance, it is extensional. So what does that mean? In our setup here with first-order theories and ordinary category theory, we model relations of subobjects and not as general arbitrary arrows. That, though, does happen when we do higher category theory and interpret homotopy type theory, univalent intensional type theories in some higher categorical context. So, for instance, if we look at the classical situation, then we have the identity relation, which over an object C is interpreted as the diagonal, right, of that object. So this is our sort C, and we think of its elements as formulas of that sort, and this value consists exactly of, if we think of this as terms, then it doubles the term, and then it says that it lies in the image, the map here lies in the image if only these two terms are equal. In the higher setup, the identity relation is now given by, we take two terms of our sort C, and then we look at the type of identities sitting over here, right? So we don't just say yes or no, they are equal or not equal. We want proof that they're equal, right, in case they are. So this guy here is in generally not, in logical terms, -1 truncated, which is to say that the whole arrow here is not monic, right? Indeed, in the usual model theory for these sort of type theories, we go via homotopy algebra, and then these arrows are in fibrations, right? And these fibrations are generally not monic. So this poses the question for a suitable notion of topology on a higher category theory, on a higher category of logical structure, right? So to capture the associated semantics with a view to this lemma here, right? Because that's on the board. In the beginning, I said that if every C has an underlying theory, and the models of that theory in D is exactly up to equivalence the kappa geometric functors from C to D. So these have semantic purpose. And so we could look at this part instead and ask what should be here, so we have corresponding sensible semantics on the other side. And so the idea will be to consider not just colimit covers of sub-objects, but structured colimit covers of arbitrary arrows. Right? So if we continue for one more comparison, the classical situation with the new situation, then what we have here is jointly epic family, and what this gives us in C. Then in the category of pre-sheaves, we can take the formal co-product of the representables of the representable of C, and we can factor this guy for its image. So let's call this whole family D. And this is the associated covering sieve to this jointly epic family, right? So these are usually, if we phrase Gordon topologies in terms of certain collections of sieves, then these are the generating sieves for our Gordon topology. And this again is a mono, right? And in particular, forgets all like non-propositional data by design. So what does that mean, right? So if we look for example, we have here our object C, and suppose we have let's call it G better. We have an arrow in C from B to C. Then what does it mean to give you a general element into our sieve? It is just again a yes or no question, right? It's just a lift here is just the information that G factors to one of the YCIs. In particular, any two such lifts are equal by design, right? There's only up to there's at most one lift to this covering sieve. On the other hand, what we could do is consider topologies or covers, let's say covers, of the form like this, right? For a certain suitable class K of diagrams. So how would this compare with our little drawing on the other side? Start here. Right? So here we compare the formal colimit in the pre-sheaf category with the colimit, if it exists, of course, in C, right? And then suppose we are given an object G into the colimit F. Then again, an arrow from D into the colimit, because representables are tiny, this again corresponds just to an arrow into one of the components, but there may be many such lifts, right? If we have another lift into the colimit, that may be a lift into another Fj, and we have identifying them with formal colimit is much more complicated. So there may be many more such lifts. Indeed, I mean, the equalizer of any two such lifts is generally not monic. at least when we are in the high categorical setting. So accordingly, you may then define the category of K sheaves to be the contravariant functors. And now, in the ordinary categorical case, it would go into set. In the infinity categorical case, we go into spaces, such that F preserves K limits. Right? So the limits of the functors which are contained in the class K. So independently of all these logical concerns before in the beginning, there's an interesting question for which class is K. This guy here, sitting inside C hat, actually gives us a topos. In this case, an infinite topos, right? So by definition, that means there is a left adjoint to this inclusion, which is left, right? So preserves finite. So yeah, what kind of classes K could we consider? So this is a hard question, this is an easy question. So let's be naive. And first, consider K to be all diagrams and see such that the common exists, right? Now, if C then is, for instance, locally presentable, ignoring size issue for the second, then it is a standard theorem that, again, every representable is limit preserving, right? And if C is not representable, this in fact is an equivalence already, right? So that means that if C was an infinity topos to start with, this will not be an infinity topos either, right? So we fail to obtain a topos. So this is a bit too much you're asking for, unless you start already with a topos in the first place. Example 2 is, suppose C is extensive. So that means that it has finite, or if we say kappa extensive, kappa small. Now coproducts satisfying some conditions, like they have the coproducts are disjoint, pulled X along coproduct inclusions exist, and I think that's it. Then one can show, if C is extensive, then we can consider the class K to be just, well, the sorts of diagrams we have under control, given the properties we impose on C, right? So we look at discrete diagrams in C. Now then we can consider Cop K then corresponds to the coproducts, the formal coproducts in the pre-sheaf category, which is the representable of the coproduct in C. And then one can show that the sheaves for this guy are exactly the classic extensive sheaves for this guy. So sheaves for the extensive And in particular, not in particular, but we can also one can show that so this is in particular an infinity topos, and it's extremely well behaved, it's super tame. And so what we see is that first trying to do something structured and then looking at a very easy case, what we obtain is actually something that is equivalent to the unstructured case, right? It's kind of boring. So the lesson here is that if we ask for too little, then we get nothing new. And if we ask for too much, then in general we get no infinity topos. Right? So we have to somehow balance our needs and our wants. So what I now want to look at is exactly a room in between those guys, namely the higher geometric sheaves, or the higher geometric covers, and the sheaves that will then be the higher geometric sheaves.
Sorry, these cases, these were categories or infinity categories?
Yeah, I didn't say much to that, right? So I started opposing those two here, and then I stopped doing that. But I'm thinking infinity categorically here.
Mm-hmm.
Yeah. But actually, everything here also holds. What I wrote down also holds for one category. So the aim will be define a notion of higher kappa geometric category, which embodies that intuition that I tried to convey in the beginning, or at least the motivation as well. And then find a notion of cover, which gives us an infinity topos, and which is related to the ordinary geometric sheaves on it, and also yields theorems, of course, that you would expect from it.
So can I just ask, so can you say what you've defined so far is, like you say, if you have an infinity category and maybe some co-limit type diagrams in it, you can define a sheaf on that to be one which sends those co-limits to limits, basically, or equivalently sort of inverts the maps from, you know, if you go to the pre-sheaf category, inverts the map from the co-limit to the representable.
Yeah, exactly.
And now the question is to define what these kappa geometric categories are, or some particular good infinity categories with appropriate kinds of co-limits.
Exactly. Okay. So in the end, we obtain an infinity topos, and that infinity, and then we want to study that infinity topos and see if that we actually made the sensible thing.
Mm-hmm. Okay. Thank you.
All right. So let me just write down the definition. So remember the definition that we made at the beginning. Now we make a following definition. Let's start with the regular cardinal kappa again, and say that an infinity category C is kappa closed, so this is standard notation, if it has all kappa small columns. So remember the case of, well, let me finish writing down and then say things to that. Furthermore, a kappa closed infinity category is kappa geometric. If it has fullbacks, and furthermore, kappa small colimits are universal. We'll say what that means in a second. And thirdly, the kappa geometric fifth category. C is the kappa logos. And furthermore, kappa small colimits are effective. Okay, so let me go through this definition. First, let me explain what I mean by universal and effective. So, if we are given a diagram as in C, what we can consider, and the colimit exists, right? So, say if this is kappa small, then we can compute its colimit, and then we can get the slice over the colimit. And on the other hand, so this will, what is an element in here? Some arrow for the colimit, right? What we can do is look into the slices of the components, and we have a map from here into each such of these guys by fullback action, right? And because we have that for all in a coherent way, we have a natural map from this slice to the limit of these slices. And this is called the restriction along that. But there's also a map in the other direction. Namely, if we have an element in this limit, this is for every component if I and arrow in here, then what does it mean to be in the limit? One can compute that the objects in here are exactly the natural Cartesian transformations over the functor F. And then we can take the colimit of the whole natural transformation and get a map over the colimit. And you can show that these are always joined to each other. And then to ask that, wait, I said this is the right joint, so this will be a co-unit, I suppose. Then, for the co-unit to be an equivalence, is to ask for universality of colimits. And to ask for the unit of this to be an equivalence is to ask for effectivity. And this corresponds to, the more common notion of universal colimits, in case you've seen that. Okay, now, the idea here being is that we use that idea of the kappa geometric 1 category and get rid of the idea that we only want to handle colimits of sub-objects, but want to handle colimits of arbitrary arrows, right? So instead of asking for kappa small unions, we ask for kappa small general colimits. And we want these colimits to be fullback stable, which is exactly the universality condition, right? And then we can ask furthermore for effectivity of these colimits, which corresponds to the notion of a pre-topos in one category theory. And indeed, this notion of a logos in this context here has been introduced by Hanel and Joyal in their topology paper, topo-logique paper. And what we do here is just stratify it along cardinals, so we can work with small things and localize at small things and stuff like that, right? And yeah, this is all, this whole idea, this is the idea of descent, and this is also covered for logoe in the paper by Hanel and Joyal. I use their notation here. Any questions to that?
Can I just ask if you have the analog of geometric, say for all kappa, is there a problem here with
It's not a priori, right? You can just put that there. Indeed.
And does it make it small? If you have a
this category, you will then have a large category. You will then have a locally small but large category. You can take, so example, any infinity topos is a geometric infinity category. It's not small, but it has descent for all small diagrams, for all kappa small diagrams for all kappa. Does that answer the question?
Could you say that last statement you made again?
An infinity topos E is a kappa logos for all kappa.
Right, okay. Okay, yeah, sorry.
Yeah? Indeed, infinity toposes are characterized as the locally presentable infinity categories which satisfy descent, so they are exactly the locally presentable logo E.
Okay, there's actually a question here in the chat. George Raptis is asking, is every kappa logos the kappa presentable object of an infinity topos for some kappa?
I don't know. But it could be. Yeah, thanks.
Okay.
That's a good question. Okay, so let's now think about what could be a cover for this, right? For these guys. Now that is let me just hit you with what I came up with. And then justify it with the following propositions and theorems. So, notation. We consider S infinity as to be given as via a combinatorial model, namely that S infinity be the coset generated by this lattice here, or this graph, sorry, this graph. So we have two rows, such objects, and then we crisscross them. And that goes on to infinity. Right? And this is a model of S infinity that actually also pops up in different parts of higher topos theory. MNL's work, and also in Dogger, Isaacson, Hollander's work. It's a Fisher free sheaf. So given that definition, it can define Sn to be just S infinity truncated at n, right? So we have x0 to xn, and then cut it there. So in particular, S0, there's these 2 points, right? And S1 can be written as this, right? All right, furthermore, we define the disk to be the join of Sn with a point at the end. So this is the coset generated by this diagram here. So we have these crisscrosses up to n, which is Sn. And then we add an x plus 1 at the end. Okay. So given this definition of spheres and disks, you can consider for diagram or map or path, whatever you want to call it, from Sn into some category, into some infinity category. So then for a map, you consider the following. Mainly, on the one hand, you can look at all higher disk maps into I, which sits vibrantly over these n-dimensional paths in I along the restriction. Via the restriction along the inclusion from Sn to Dn plus 1. Here we have the vertex P. And then we can consider the Dn plus 1 extensions of P by this program. So this is the infinity category. So here's a P. And if we think of when P is a map from the Sn into I, which is two copies of the Dn minus 1 glued together along the boundary, right? So we can think of these as two paths with a common boundary, and then this consists of the fillers, right? These are the homotopies. This is the infinity category of homotopies between these two paths. Right. Then the definition. So let's suppose let's see the kappa closed with pullbacks. And then I in the small with kappa small infinity category, also with pullbacks. Then we say that a functor or diagram is a higher covering diagram if cliffhanger. Two conditions hold. First, F preserves pullbacks. Okay, that's very short. And secondly, it will be a homotopy lifting condition in some sense. So, if for all such higher paths in I, we have a canonical map of the following form. So here we can look at these extensions of P in I. Okay, we can evaluate them at their point up there. Then we can push forward that with F. And now each of these elements, right, each of these extensions not only gives us an element with the colimit of F, but we can evaluate each of those vertices and consider the final product of the lower dimensional vertices and so on until we end with the base vertices over the colimit. And on this side, we take the colimit because it exists for every such extension. And the condition is that this canonical map is an equivalent. So intuitively, we want that all higher homotopical data of the colimit can be computed entirely using homotopical data computed in I and push forwarded along F, right? So these pullbacks here, right, they consist, I mean, the lowest dimension of pullback here consists of vertices in these two components together with a path which identifies them in the colimit, right? And I want to be able to compute that path using a path from I. Now, the according theorem is that if kappa is regular, then C is small and kappa geometric, then we consider class K infinity to be the kappa small high covering diagrams. High covering diagram. Then the sheaves for this class, which is defined again as the localization at this, at what I defined as called, depending on the class K before, right? Which the comparison of formal colimits in the appreciative category to the representative of the colimit in C. As a subclass of appreciates is a left exact accessible localization. So in particular, it's an infinity property, the sub-infinity property of this guy. And the idea how you show that is you want to show that this set here is a basis of some form, and hence generates such a left exact accessible localization. And in order to do that, one can use, I used Annette and Dina Supermanium's work on modulators. To show that it goes under certain operations. So the idea is you have to show that the identities of representables are contained. And this is true because the constant functors are higher covering diagrams, and pullback stability follows from pullback stability of colimits in C, and then closure on the diagonals comes from these higher spheres in C. So what has this to do with ordinary geometric sheaves?
So the sheaves are the functors which send the colimits of those diagrams to limits.
Exactly.
I'm only saying it because that's the way you define sheaves earlier without mentioning localization and stuff. So well, I mean it's the same thing, right?
Yeah. Okay, so if we start with a kappa geometric infinity category, then for kappa small set, we can consider an associated simplicial set, simplicial kappa small set, right, by just taking the nth power of that set. Let me put it here. And so we obtain this kappa small simplicial set and an associated discrete vibration by the Brody construction. Fibers over delta. And then we may consider diagrams of this total category. Into C. So, with the following condition, namely, such that for all of the integers, all according to type sequences in X, the natural map on this tuple here, which is the general element of our group construction, into OX this form. of its coordinates. Such that for all this map is the natural here is an equivalent. Okay? And then we can consider the class K1 to be K prime. I'm not sure exactly what I intend to eventually. To consider all the tuples of this form where f and x is as above, right? So x is a couple small set and f is a functor of this form. So one can consider cos kappa 1 to be the associated class of arrows in the sheaf category as I defined before. And then one sees that actually these are all monos and that this is a basis for the ordinary kappa geometric Gordon topology. One sees. So I will not have time to illustrate the argument. But so what we see is that the following lemma. So first of all, we can see that the ordinary geometric sheaf condition is captured by this more general idea of preserving limits, taking colimits to limits. What we can in fact show that if we consider these sheaves for higher covering diagrams, then this sits inside the sheaves for, did I write this down correctly? Yeah. This is not line. Sits inside the ordinary geometric sheaves for C. So that means that every higher geometric sheaf is in particular an ordinary geometric sheaf. Okay? And this proof would actually be straightforward if delta would have pullbacks, delta up would have pullbacks. It doesn't. But one can remedy this by replacing delta with finite non-empty sets, which does have push-outs, so its opposite has pullbacks, and then do everything instead of delta up over a thin set plus up, using that this simplicial set that I defined there is actually symmetric.
Maybe I can ask you while you're rubbing that out, just George Raptus also asked, well, so you show that you can construct these infinity topoi, right? Certain localizations, if you look at these higher covering diagrams, and he asked if that localization is topological.
I come to that.
I thought, yeah, okay, good. I just saw you rubbed it out, so I thought.
Yes. Yeah. So, yeah, I'll skip then the definition of what topological and cotopological is. I suppose I'm running out of time anyway. So, proposition if C is kappa geometric, and you can show first that you have the localization to ordinary geometric sheaves, which is by definition topological, because it was the localization at a Groton topology. And then we have seen that inside that we have the higher geometric sheaves. One can show that this is cotopological. Right? So the ordinary geometric sheaves are exactly the topological part of this general localization. So in particular, these two sheaf theories only differ by a class of infinity connected maps. So the difference is very subtle, but it is crucial. So one can show that this co-topological part is generally non-trivial. And so by essential uniqueness of these factorizations, this is generally not topological. There's the first two. And then 3, to anybody who knows what that word means, we can furthermore show that, sorry, this is infinity. That one could ask, well, maybe this is the hypercompletion of the ordinary geometric sheaves, but it's not. Generally not hypercomplete. Okay, so to...
Did you write generally hypercomplete there?
Yes.
Okay.
Yes. So particular corollary is that points of the ordinary geometric sheaves are exactly the points of the higher geometric sheaves because the infinity category space is hypercomplete and you cannot tell the difference between things that only differ by co-topological part. So lastly, then let me finish this talk with one theorem, with the statement of one theorem. Namely, one has the following lemma that, so the problem being that higher covering, this long condition there, condition 2 of being higher covering looks like it could be quite complicated to verify. But I introduced the notion of the kappa logos, right? I introduced the kappa, the notion of the logos was already introduced by me.
Did you say, sorry, George Raptis is asking, I was in your, so did you say it's hypercomplete or it's not?
It's not, it's generally not. Oh, sorry.
Yeah, okay.
So sorry, yes. My bad. Thanks. So suppose C is a logos or a kappa logos. Then for kappa small categories I with fullbacks and diagrams from I to C following are equivalent. So F is fullback preserving, right, which was one of the two conditions in the definition, and 2 is maybe an awkward way to phrase it, and this high covering. So what I'm saying is, if C is a kappa logos, then the second condition is vacuous. It is always automatically satisfied. In the case that these columns are effective, right? So then we can show the following theorem that we ended the first section with. Every infinity topos D is the infinity category of higher geometric sheaves over itself. So that means that functor, i.e. a functor from E into small spaces is higher geometric if and only if it is representative. Which of course, because both categories are locally presentable, means if and only if it preserves small limits. So we recover, at least in this case, where we look at the codomain being small spaces, we recover Lewis' sheaf condition, which he defined on infinity toposes to be preserve all small limits. And part of the theorem, which basically comes from part 2 of the proposition here, is that this is not true for the ordinary geometric sheaves on infinity topos E. So, yeah, the statement being there are infinity toposes such that E is not equivalent to sheaves to the ordinary sheaves of itself, right? But it is always equivalent to the higher geometric sheaves of itself. And so this suggests that this is a, well, I don't know if this is, in the end, it will turn out to be the right notion for various aspects of the general theory, especially when it comes to a syntax semantics kind of correspondence that you would want to have if one was to develop eventually a notion of classifying affinity toposes. But the theorem, like this theorem here, and this closeness to the original definition suggests that this might be on the right path. And I hope to continue the research. I will publish a paper about this very soon, and then hope to figure out if this syntactically is also the right thing to do. Thanks for your attention.
Thanks very much for a great talk. Any questions either online or in the audience? Maybe I'll just first ask one that's online. From George Raptis, he asks, can one describe higher coverings in terms of hyper coverings in some way?
I don't think so. Yeah, I'm not quite sure about that. I thought about that question for a minute, but not for two. So I can't answer the question. But I'm not quite sure about the role hypercovers play in this context at all. To be fair, simply I don't know. So.
Okay. Christoph?
So maybe is that corollary true more generally? So is it true that the coupled geometric maps from the coupled geometric category to an infinity topos are the same as the infinity topos maps from that topos to these sheaves, K infinity sheaves over that coupled geometric?
It depends on what you mean with the view. So I didn't define what a coupled geometric functor is, right? So I'm not sure, it probably depends on how you define what that exactly means. Because you could define it to preserve all small co-limits or all coupled small co-limits. You could define it to only preserve the co-limits of higher covering diagrams. Right now, if you only want it to preserve the co-limits of higher covering diagrams, then that basically holds by construction. Again, just by the usual Frank Stenzel kind of argument thing. So a priori, it will depend on how you define the notion of a coupled geometric functor. Maybe it doesn't in the end. Maybe you can show that these are actually the same things because you have that Cartesian, right? You also expect your functors to be left exact. So maybe that makes a difference. I'm not sure.
Any more comments or questions, either here or online?
Is there any relation to also the perspective that's in this topology paper, where they're sort of viewing toposes as algebras for some distributive law between species and finite limits? Because some of these conditions are very much like exactness conditions in the heterogeneous thing, and I'm wondering whether that gives a nice perspective in some of this that isn't evident from the way you can make it say that.
I mean, I'm not sure in which direction the question goes. I mean, the way I understand it, it would be probably tied to Christoph's question in the sense that how we define a coupled geometric functor to be defined. I'm not exactly sure how to. I don't think I answered the question.
Yeah, I can answer in more detail.
Okay, yeah. No, probably maybe you don't. I mean, I know what you mean when you talk about the walking and whatever, but I don't know what this relates. So yeah, maybe you can extend that.
Any last questions? If not, then let's thank Raffael again. And that's all for today.